Dear colleagues, dear friends, this is the greatest honor for me to become a recipient of the prestigious George Zaslavsky Award. I'm very proud to join the corps of awardees, including Thomas Solomon, Raul Nigmatulin, Sergei Prantz, Mark Edelman, and Xavier Lencini. I met with George Zaslavsky in 1998, 2003, 2006 during his long stay visits to the Centre de Physique Théorique Marseille à Lumini in France. He was one of the key persons in the theory of dynamical chaos, but also made important contributions to a variety of other subjects. And I admire him not only for his open-mindedness and profound scientific achievements, but also for his active social position in 1960s when he was signing letters in defense of many Soviet dissidents. His personality influenced me very much. My talk entitled How Structure Creates Force. It is devoted to statistical ensembles of ergodic walks in finite and directed graphs, relevant entropic variables, navigability of graphs, and the two graph nodes. But I would like to start with a bit of philosophy. The probability we assign to an event depends on whether we count it as a one of many, considered all at once, or not. In other words, an estimated likelihood of events hinges on their assumed membership in an ensemble described by some probability distribution. The famous two-child paradox by Gardner serves a good example for this point. Mr. Smith has two children. At least one of them is a boy. What is the probability that both children are boys? On the one hand, as the probability of getting a boy equals 1/2 uniformly and unconditionally for all families, using Bayes' theorem, we obtain that the probability of having at least one boy in a two-kid family will be the same as just having one boy. Namely, the conditional probability of having two boys, if there is already one in the family, equals the conditional probability of having a boy in the family of two boys, that obviously equals 1, times the probability of having two boys independently divided by 1/2. The probability, that is the probability of having a boy, P1 equals 1/2. On the other hand, as having a boy in an ensemble of two-child families with at least one boy obviously comprises three possible events, namely boy and boy, boy and girl, girl and boy, 1/4, 1/4, 1/4, 3/4 altogether. And therefore, the same Bayes theorem tells us now that the probability to get another boy in a family of two is 1/3. The ensemble interpretation in which each admissible event in a family of two with a boy appears equally probable is preferable in the context of ergodic hypothesis blind to family history. Namely, in the context of two-child paradox, there is no way in probability theory to discern if the gender composition in such a family stays put, or children change their sex, exploring possible gender identities during an infinite lifetime, provided at least one of them always stays a boy. The ergodic hypothesis helps to avoid this awkward question by equating the ensemble and time averages while replacing a dynamic description of identity changes by the probabilistic description within the ensemble over a very long time. Switching temporal and ensemble perspectives under the spell of ergodic hypothesis is assumed in thermodynamics, equilibrium statistical mechanics, and the theory of dynamical systems. Nowadays, all major events related to probability theory and statistics happens in the field of financial mathematics, and the stock market guru and an author of many bestsellers, Nassim Taleb, put it right: there is no probability without ergodicity. If you try to apply probability mindset, not in an ensemble perspective, your results might be erroneous. Ole Petrens, an economist and co-author of Murray-Gell-Mann, a Nobel Prize winner who died in May 2019, now works on a non-ergodic version of probability theory, so to say. The concept of ensembles and ergodicity have a long history. Boltzmann introduced a monode, a family of possible stationary probability distributions over a single cyclic trajectory of a system on an energy surface in the phase space as early as in 1844. According to the Boltzmann hypothesis, the time spent by a system in some region of the phase space is proportional to the volume of this region, so that all accessible microstates are equiprobable over a long period of time. Originally, it was an idea of Isaac Newton. He proposed to use the center of mass method to simulate the behavior of solids, liquids, and gases. All masses should be concentrated at a single point, the center of masses. It took then 1.5 centuries until this program has been realized by Ludwig Boltzmann in his thermodynamics, in the concept of monode, a single trajectory describing the whole composition of molecules or particles in the gas. The next step had been done by Hermann von Helmholtz in 1895 when he introduced his concept of Gesamtheit, a statistical ensemble, as we would call it now. Finally, in 1902, Josiah Willard Gibbs coined the concept into the English-speaking world. If for Helmholtz his Gesamtheit was only hypothesis, a point of view, one among many, for Gibbs, a statistical ensemble was already a law of nature. In my talk, I want to review three major statistical ensembles: microcanonical, canonical, and grand canonical, and show you that the ergodic probabilistic mindset might be applied not only to particles of ideal gas, but also for some quite abstract mathematical objects like graphs. Let me remind you that each statistical ensemble is characterized by some set of conserved quantities. The microcanonical ensemble assumes the conserved number of particles, volume, and energy. The system is assumed to be isolated. The canonical ensemble means that the number of particles, volume, and temperature, so to say the distribution of kinetic energy over particles, are conserved. Finally, in the grand canonical ensemble, volume, temperature, the distribution of kinetic energy over particles, and chemical potential, the intensive free energy per particle, are conserved. The number of particles might change in the grand canonical ensemble, and the system is therefore viewed as open. We will discuss walks on finite connected and directed graphs. First, graphs are ubiquitous data models used nowadays broadly in machine learning in any other application. Meaningful graphs and relevant data sets are always finite and even relatively small. For instance, there are 96 canals in the city of Venice, and they are not random. There are just about 10,000 nodes in a spatial graph of the city of Lubbock, where I live. The thermodynamic limit in our approach goes along the length of walks. This is an obvious idea. Any finite graph provides enough room for infinite walks. There is an opposite approach known as complex network theory, the Barabasi-Albert preferential attachment, scale-free graphs, and related phenomena. They exploit another thermodynamic limit in the number of graph nodes. Their graphs are infinitely large and therefore presumably random. With a probability 1, an infinitely large scale-free graph is a tree. Lack of auxiliary connections and feedbacks, no loops. Real-world graphs are not random at all and have a lot of loops and cycles, critically important for their functionality. The macrocanonical ensemble of walks is defined by assigning equal probability to every path of length n in the graph. In the d-dimensional lattice, the number of available paths grows exponentially with n, and we readily transform it to the standard statistical mechanic notation. The Helmholtz free energy equals nd, temperature and the Boltzmann constant is the inverse natural logarithm of 2, as free energy is the, by construction, is the Legendre transformation of the internal energy with temperature as an independent variable. It follows that all volts in the microcanonical ensemble uniformly have zero energy. The same result follow for k regular graphs as well. Substituting logarithm of the base of 2 of the number of neighbors k instead of the space dimension d, we might easily extend the results to regular graphs also. The chemical potential of an edge absorbed by a very long walk in a microcanonical ensemble equals the effective dimension of space in a regular graph. In a general case of a connected and directed graph described by an irreducible adjacency matrix A, such that which is 1 if an edge belongs to the set of edges and 0 otherwise, we apply the eigendecomposition of the adjacency matrix and factor out the graph's spectral radius, its biggest eigenvalue, from the parentheses. All terms in the sum decays exponentially fast with the length of walks n, and we can omit them in the thermodynamic limit of infinite walks. The chemical potential then equals to the log of graph spectral radius. This quantity is known as topological entropy of the graph, describing the exponential growth rate of the number of indistinguishable paths with n, a measure of graph complexity. As the spectral radius in k regular graphs equals to the number of neighbors k every node has, the chemical potential fits the previous results. The log of the spectral radius plays the role of the graph space dimension in the macrocanonical ensemble, indeed. Let's talk a bit about applications of the microcanonical ensembles. Missing nodes and edges might dramatically reduce the number of long paths available in a graph, reshaping the global mobility patterns. A missing node reduces the number of very long paths in the graph and therefore reduces its free energy by the following amount of energy corresponding to the number of very long walks starting or ending at I. We call the resulting quantity entropic pressure, as it accounts for the local stress characterizing the transfer of Walker's mobility from the node I to the rest of the graph if I is not available. Similarly, by eliminating an edge, ij, from the graph, we reduce the number of paths of length n available from I by the number of paths of length n minus 1 available from j. The direction-dependent entropic force emerges from the statistical tendency of very long walks to follow the preferential transition to the neighboring nodes, hosting many infinitely long paths. Such a random walk is known as a Reuel-Bowen random walk in among mathematicians, or is maximum entropy random walks in the physics community. The entropic pressure pattern in the membrane with a defect is concentrated at its structural center on the left-hand side. The related entropic force pattern is illustrated by coloring nodes accordingly the elements of the Perron vector of the entropic force matrix, indicating the highest force magnitude at the low dimensional borders of the membrane, especially in the corners. We further illustrate the directional aspects of the entropic force by coloring nodes accordingly the elements of the second major eigenvector, Fiedler eigenvector of the entropic force matrix. Fiedler vectors are used for bisection of graphs and show the major gradient of the force in the city map. We have drawn the spatial graph of Labac taken from the Open Map service. The entropic pressure shown on the left-hand side is non-zero at the structural center of the city and zero everywhere else. This structural center is now located far apart of his historical center. The structural center is absorbing Walker's trajectories, as the entropic force is negative there. And it's positive, the Fiedler vector is positive in the band toward the historical city center, anchored at the abolished city railway station. Trajectories are expelled, trajectories of microcanonical ensemble folks are expelled from that region, and the Fiedler vector is zero else, everywhere else. So in overall in the city. The United States is a land of traveling cities. Also, railway construction enhanced the city status of Lubbock in early days. Its maintenance has a continuing negative impact on the urban development since railways barricade streets, dramatically cutting down the number of possible paths people can drive or walk, and creating neighborhoods isolated from nearby areas. The large urban voids in North and East Lubbock remain cut off by rails and industry, pushing the city life away from the angle formed by the wearing railway tracks. The city grows to the southwest anyhow, running out from the loop 289 that marks the old city boundaries of 1965. The red-colored region in West Lubbock, on the right-hand side, absorb the lion's share of all possible infinite roads in the city. Wherever we go and whatever we do, we are going to go through the places colored in red. Not surprisingly, most viable commercial ventures and businesses, as well as high-end properties, reside in these well-integrated quarters where people plausibly meet each other by chance. In contrast, the blue-colored areas of the city downtown and the industrial areas in North and East Lubbock incorporate just the evanescent share of possible life troubles. A canonical ensemble represents the possible states of a system in equilibrium that does not evolve over time, even though the underlying system might be in constant motion. The canonical ensemble is a collection of microstates, the presumably long walks of length n, compatible with a specified macrostate at discrete probability density function pi. So canonical walks, ergodic walks, are those which can be characterized by some stationary probability distribution. The total number of walks lumped into the pi macrostate is then given by the multinomial coefficient, which grows exponentially with n with the rate h, that is the entropy of h walks. The chemical potential of pi walks equals its information content, the uncertainty of the location of the walker in the graph. A family of intrinsic random walks constitutes an example of canonical ensemble of walks in the graph. Let us introduce the nth order degree of the vertex I as the number of walks of length n available from the node I. The nth order degree evolves under the action of the adjacent symmetrics A. For each n, there is a transition row stochastic matrix in which all paths of length n are taken with equal probabilities. The first order walks are isotropic, usual random walks, in which all nearest neighbors are chosen equiprobably. The infinite series of such intrinsic random walks converge to the Reuel-Bowen transition operator, in which all infinite walks anchored at a node are chosen equiprobably. Isotropic usual random walks, in which all nearest neighbors are chosen equiprobably, uniformly covers all nodes of the membrane. Its stationary distribution is uniform over the regular graphs. In contrast to it, the Reuel-Bowen random walks are confined in the structural focus, the most central and most integrated part of the network. The spectral gap of Reuel-Bowen random walks is maximum over the canonical ensemble of walks, so that the convergence to a stationary distribution is the fastest for the royal born and the random walks, and the mixing time toward the stationary distribution is minimum. The relative entropy rate can be used for measuring information divergence over the canonical ensemble of intrinsic random walks in connected and directed graphs with the length of walk n, and as a measure of graph structure anisotropy. The graph space dimension tensor may be used for assessing the degree of directional anisotropy in transitions when all paths of length n available from the node I are chosen with equal probability. For n equals 1, the graph space dimension tensor reduces to the graph space dimension itself, logarithm of alpha, and in the limit n to infinity, it takes the form compatible with the microcanonical space dimension of the graph. So if with respect to microcanonical ensemble of walks, the space dimension of the graph is the logarithm of its spectral radius, for a canonical ensemble, the space dimension is a tensor, which includes also, so it's a logarithm of a spectral radius, but normalized by the element of the Perron eigenvector of the node I divided by the Perron vector element of corresponding to the node J. The problem of effective navigation in graphs and networks can be considered with respect to a canonical ensemble of walks, as an effective location prediction requires a density of locations will be known. Frequently used sites are predicted more efficiently than little frequented, especially in the long run. Bayes' theorem describes the probability of navigator's present location x based on the prior knowledge of her previous location n steps before. So the density of n step precursors for the location x induced by the density of walks pi. The expected amount of information about visiting the location x at present is scattered over the entire graph in the past and can be assessed by observing all possible pi steps and step precursors x negative n. The amount of predictable information is bounded by the information content of the pi walk defined on the graph. However, the actual amount of predictable, navigable, so to say, information about present navigation location may be much less than the amount of information revealed at every step of the canonical walk. Graphs may have disparate degrees of navigability by different walks. The information function can be represented as a sum of the predictable and unpredictable information components. The predictable part P assesses the amount of apparent uncertainty about navigator's location that can be resolved with some navigation strategy compatible with the pi walks. And U estimates the amount of true uncertainty about navigator's location that cannot be inferred anyway. In what following, we attribute the predictable information component P to the navigability of the graph by the P walk. Both information components should have the same form as the information function, with some partition functions phi and psi, such that the stationary distribution of random walks P is nothing else but the product of phi and psi. We call the partition function phi the navigability to the node S in the graph by the pi walks. The information function I can be decomposed into three components. First, the excess entropy assessing the expected amount of information consisting in the whole infinite motion history of the walk. We can attribute it to the path integration navigation strategy. Second, the conditional mutual information between the present and future locations that depend only upon the immediate past location x, t-1, but not on the entire historical sequence of the locations visited by the navigator in the more distant past. We can attribute it to the landmark-based piloting navigation strategy. Finally, third, the remaining information component, U, exists only now being neither a consequence of the past nor having any repercussions for the future. It assesses the amount of true uncertainty about navigators' present navigator's location and cannot be resolved by any rational navigation strategy. For a random walk defined by a row stochastic transition matrix, the degree of navigability of the graph and the navigability to a node can be readily calculated. Navigability to graph nodes over canonical ensemble of walks depends upon the graph structure and the random walk chosen for exploration. On the left-hand side, we have colored the membrane nodes according to their navigability by usual isotropic random walks. The best navigation is pertinent to the border nodes and those at the membrane corners. On the right-hand side, we have shown the navigability of the same membrane by the Reuel-Bowen random walks. These walks are confined to the central part of the membrane, and therefore the best navigability is attained at the central point, simply because the random walker stays there most of the time. A grand canonical ensemble represents the possible states of an open system exchanging energy and particles in thermodynamic equilibrium with a heat bath. In ergodic walks, the grand canonical ensemble describes fluctuations of the number of distinguishable very long walks anchored at a node about the chemical potential of such walks calculated over the entire graph. The probability distribution of such fluctuations is the distribution of the Fermi-Dirac type. This distribution should be perfectly localized. It should be zero everywhere, excepting for some nodes where the system is open. The Fermi-Dirac is non-zero where the system is open, where the city of Lubbock, for instance, is under construction in the south part of the city, in south suburb, and well, zero everywhere. Conclusions. The ergodic probabilistic mindset might be applied not only to particles of ideal gases, but also for some quite abstract mathematical objects like graphs. Missing nodes in the edges might dramatically reduce the number of very long paths available in a graph, reshaping the global mobility patterns. We may formalize their effect as action of entropic pressure and force acting on trajectories. The problem of effective navigation in graphs and networks can be considered with respect to a canonical ensemble of walks, as an effective location prediction requires a density of locations be known. Frequently visited sites are predicted more efficiently than little frequented, especially in the long run. Fluctuations of the number of distinguishable very long walks anchored at a node about the chemical potential of the n walk is non-trivial where the system is open, where the city is under construction. Thank you so much for your attention. So